Thank you, Brian, your kind introduction, and also thank you, Shai, and for organizing this symposium, inviting me, sharing my research findings. Today, I'm going to talk about, can you see the AI base? What is AI stand for? The reason I'm asking, this is the Poultry Science Society, right? This is not avian influenza. This, yes, this is artificial intelligence, okay? So I want to make sure I'm talking about the AI, how we can utilize the AI technology for our research in poultry, okay? This is about. Of course, I think I'm going to introduce our research journey in terms of hyperspectral imaging past the 2 decades. So I'm going to show a couple of slides to what we have done and what we are doing and what we are going to do for hyperspectral imaging technology development in poultry industry, okay? My talk in about, I'm going to briefly introduce our areas, hyperspectral imaging research work. And also, thank you to Joseph. You just gave a very good introduction about hyperspectral imaging, but I'm going to focus on the how we can utilize the hypercube from the data into our model development. And in that case, I'm going to introduce about hypercube from foodborne pathogen. This is a little bit challenging to collect the live bacteria, the hypercube. So I'm going to show some our experience, how we did. And after that, this is the main part. I'm going to talk about the deep learning method, specifically FusionNet. This is a multiple model. We just combine the different hypercube because hypercube has many different features. So most case so far, the many scientists and researchers using the spectral data, most likely. However, still we have a spatial information such as morphological feature there, and also we have intensity distribution, right? So I'm going to talk about that. And finally, I'm going to share our experience to how we develop to AI model, in this case, the deep learning based, and we call the fusion model. So fusion models include 3 different components from hypercube. All right. The Joseph just mentioned about hyperspectral imaging has many different names. Another name is imaging spectroscopy, but basically hyperspectral imaging started in the mid-80s. It's a NASA group. They just applied the hyperspectral technology for the airborne and the satellite imaging, looking at some other terrestrial and also the surface, and there's some agricultural crop, something like that. And back to 1999, our lab actually started, we call it close-up. Just with the remote sensing area, we just looking into the lab, look at the food. So in that case, we actually looking at the poultry bird. And in here, the picture at the top, that is we call the first generation hyperspectral camera. At that time, no commercial hyperspectral camera is available in the market. So we just assemble all these components ourselves together, and then we just collect the binary data, okay? The binary data means we cannot see anything, the data from there, just a 0 to 1. Okay, so we just combine those binary data compiled together using some methodologies, convert to hypercube. That's actually hyperspectral data. However, in this particular system, still line scan. When it's a scan, line scan means either object move or we have to move the lens. So we cannot see the object at all. We can see on the line. So main challenge is how we can convert this binary code into the image. So we did. Okay, this actually, I'm going to share that image later. And then the bottom picture is about multispectral camera, because hyperspectral image is still lots of data. Most data is highly correlated to each other. That means it's redundant. So we just select the most key wavelengths important, the data only. And specifically, the reason we just developed the multispectral system here our goal is actually to implement this system into poultry plant. How can use the hyperspectral camera in the real time? We cannot. So that's the reason we just pick only 3 wavelengths from hyperspectral data. That is 517 and 565 first. To wavelength ratio give us fecal contaminant. That is the oxymicrobin band. So it makes sense. If the skin is really touches on the fecal matter, in this case, we just detect the fecal contamination. We can see the fecal detection there, okay? Let me show the one example. When you look at just a single wavelength band ratio, we can see only fecal spot only. But this is power of a hyperspectral imaging, okay? If we just collect this 6 hyperspectral data from chicken cockles, this is a fecal contamination there. We use the 6 different image processing tool, and finally we found the spectral angle mapper. This is low middle, okay? You see the different color. Red actually indicates duodenum. Green is ceca, blue is colon, and ingesta is the bottom. If you use hyperspectral data, not only just detect the fecal matter, but also we can detect what kind of feces. Okay, this is actual strength of hyperspectral data. Based on the method, we developed actual real-time and inline hyperspectral imaging system. The Central just tried to demonstrate real-time, but this is actually we have. Can you see all the enclosure there? The reason we made the enclosure, this is very important to implement a poultry plant because there's very harsh environment, very high the temperature and moisture content in there. Without that kind of enclosure, we cannot test on it, okay? So just keep in mind, we're trying to develop this system to implement poultry industry, not just in the lab, okay? Actually, we tested our system in plant in the poultry processing plant in South Georgia, and we tested over 100,000 birds, and it's quite high accuracy. We got almost a 90% detect. So that is still we tested the multispectral at that time, but we just already made hyperspectral, real-time hyperspectral system is ready to go, and we still keep validating that system in the future. And also we just developed, and the Central just mentioned, same concept, the push broom hyperspectral imaging system, looking at the agar media. In that case, we looking at what kinds of actually the contamination is highly correlated to some kinds of bacteria. So we just developed the agar media detection method 2010. And this is actually a highlight. I'm going to talk about this presentation in more detail. And previously, actually, the hyperspectral camera scanned the line scan based. I just mentioned that means either object move or lens move. However, when you try to apply this bacteria, we cannot do move either one. And also, more important thing is, we have a time limitation because we want to measure the live cell, live bacteria. So if we just lose the time, then all the data is invalid. So our goal is actually less than, try to get a 45 or 50 seconds, okay? So this is actually the first hyperspectral microscope based on the area scan. Area scan means hyperspectral camera can scan the area, not line. So it's very fast, okay? The frame rate is very high. So this is acoustic optic tunable filter based. We developed that one 2012, but this system still is not that high resolution. It's only give us 89 spectral band. So we continue to develop that different platform. However, I'm going to show how important to make a sample, because when you see this one, this is actual sample from Salmonella enteroides. What you can see is nothing much, right? So we have to work with optimize system, because this is very specifically the AOTF-based area scan. But our scan is based on the scattering image. Because previous speaker talking about there are several different methods to measure the data, and reflectance, transmittance, and observance. Of course, the observance is calculated by the some formula using reflectance. However, our system is actually measure the scattering based on the very specialized pattern, the spectral line, shooting the line underneath. That can give us some data like that. But initially, we couldn't get any bacterial cell very quite well. However, we optimized all the system, including lighting. You got some cell like that. So this is actually first a live cell. Keep in mind, this is a live cell. So we have to scan this hypercube 45 seconds. Okay? Of course, this scanning time depends on the integration time of the system, and also gain setting on the lighting, all different kinds of very complex combinations put together. So finally, we got a cell. Okay? So using this data, we try to develop some machine learning algorithm, but the result is not that great, because, as I mentioned, the AOTF give us 89 band. This resolution-wise is not that quite high. So we just continue to develop. This is FPI. This is the interferometer based, give us 300 band. It's a much higher resolution compared to the previous one. And also, this is very portable. We developing this system with the industry partner, and then we just developed that one. And using Hypercube data, we also developed some FusionNet AI-based model. So this is actually highlight today's my presentation, okay? I'm going to continue how we developed the hyperspectral data using the AI model. Okay. The hyperspectral data, or data cube, you can see the left corner there. This is a bacterial hypercube, okay? We use a bacteria, the E. coli, Staphylococcus, Listeria, and Salmonella put together. So you can see the surface. So that's the image. And then we have data from 400 to 1,000. It's a 300 band, okay? So hypercube actually consists of 3 components: intensity, spatial, and spectral. In most cases, they use the spectral data only. However, in this case, we just looking at the cell itself, so we can take advantage of the morphological feature as well, and also scattering distribution from the cell, okay? So this is the spectral data. We use the one-dimensional convolution neural network as a deep learning model. And this is another cell, the spatial information, okay? You can see the size or different feature. So we use the LSTM deep learning model. And finally, this is intensity, okay? As we measure the scattering information, the scattering intensity distribution is not homogeneous on the surface, okay? It's all different. So we just consider that scattering feature is another input. Okay, this is hypercube from Fabry-Paro interferometer, or FBI, and hyperspectral data. So this is a close look at. You can see that each single cell E. coli, Listeria, Staphylococcus, and Salmonella. And bottom one is a hypercube. Each one has a different spectral band image. And also, we just take a look, just compare different platform, how they closely did the spectral or some other spatial information is equal or the uniform. So left-hand side was from AOTA base, 89 band. Right-hand side is FPI base, more than 300, okay? So in terms of the shape or some other information look very similar in this case, right? And more detail, you're also looking at the spectra. The AOTF, you see the 89 band, compared to FPI. FPI is more the resolution, you can see the curve more smoother, right? But when you just compare the peak and valley, one-on-one, it's almost identical, a little bit shifted. That is depends on the, some calibration issues. We just identify, we match on it. And also we just look at the single cell, more detail. This is actually a three-dimensional scattering intensity distribution. And you can see the left cell is actually from the Salmonella hydra, and right bottom is Listeria. You can see that some scattering is the distribution looks different, right? So this is another feature for the deep learning vision and model we have. And morphological features, another one. Especially if you look at some bacteria, gram-positive versus gram-negative, the size is different, shape is different. So we just picked the 9 very specific the morphological feature, including area, eccentricity, and the maximum length, minimum length, ratio, and also perimeter, such as. Okay. I'm going to give you a little bit, very brief, just make sure, artificial intelligence, AI. AI is actually, you heard of many mass media, it's even you have the handphone, you use the AI here, right? No matter you just recognize it or not. The AI actually, we can talk about some intelligence in artificial design device, okay? This is actually the definition. Actually, the AI term is used by McCarthy about around, I think, 1956. So basically, this is two ideas in the definition, the intelligence and artificial device. This is actually AI we're talking about. So you can feel the AI, you can use the AI daily, such as the visual assistant, so social media, streaming, everybody has it, right? And then navigation, even smart car, drone, banking, even finance, and natural language process. So it's name on it. So use AI a lot. But how about the application? Okay, there are many applications we can use the AI, such as healthcare, automobile, finance, surveillance, education, even gaming, robotic, and agriculture. So I'm going to talk about the more detail in application in agriculture, okay, especially food safety. So if we just looking the AI, we just consider many different approach, such as the deep learning, classification, image recognition, and machine vision, and so on. So I'm going to use that kind of AI tool to apply my data analytic from bacteria data, okay? So deep learning, this actually the model approaching we developed the FusionNet, and deep learning is a class of a machine learning algorithm, okay? But they used multiple layer to extract higher level feature. So feature extraction is a very important step to develop the deep learning model. So I'm going to share how we did, maybe next few slides. So deep learning method, actually the information processing. So once you got a feature extract from your data, in this case, hyperspectral data, you develop some deep learning model and classify, in our case, or some prediction, some other aspect. I'm going to talk about a little bit unit architecture because this is very important in our case. When you collect hypercube, we have to make sure extract the single cell data because once you just scan some bacteria, there are several hundred cells in there. So how can look at the single cell? This is a very, very important step, very important process. Once we just collect the segmented single cell, we can extract from there spectral, spatial, and morphological data. So this reason, your unit development is very important, single cell segmentation. When you see this unit, the unit actually consists of two parts. One is the encoding, left-hand side. The other is the decoding. So in encoding part, the successive layer are used for future extraction. So that actual layer give us some future extraction. And also right-hand side, the decoding part, both encoding and decoding future are concatenate. Concatenate means if you maybe, for example, if you just extract the future from morphology and intensity and spectral, there could be the input data. So you have to align from beginning to end, one line. This is actually input line, okay? So then it's actually the future extraction is the next line, and finally we just select the final optimal feature into the our model. This is a result of a segmentation. We try to look at 5 bacteria. In this case, the first one, top one is Campylobacter, E. coli, Listeria, Staphylococcus, specifically type Murium, the D, and also, also the Staphylococcus in the bottom. The first column, there's a cell image. It's not clear because this is the hypercube, hyperspectral data. Okay? But the second column is a ground truth. And last one is a result of a unit. Between that, the third column and fourth column is the odds algorithm, and the other one is a watershed algorithm. This is very, most popular, is very traditional segmentation method. Compare that, our unit worked very well, okay? I just put up the one example in the table. In case of the E. coli, the odds give us 94% accuracy, watershed is 68. However, unit give us 98% accuracy. It's very high, okay? In addition to that, our goal is actually extract a single cell. But when you look at maybe some slide data, many cells touch each other. Some cell is a growing stage. Some cell is maybe broke. So we don't want that on. We want to get a very sound, healthy cell, okay? Our unit actually differentiate, touch the cell. Because morphological feature is very important feature we need for model. If you collect that kind of touch the cell, the morphologies keep all changing. So the collected single cell is most critical. This region I'm talking about, segmentation is very important. Okay, so based on that feature, we developed a FusionNet framework like that. The LSTM for morphological feature, the RESTNet framework for intensity distribution, and 1D CNN framework for spectral profile. It's all combined together. This is actually the FusionNet we developed for classification. When you look into morphological feature a little bit detail, you can see some information from there. For example, the top left, that is the area measurement. As you can see, the Listeria in the Staphylococcus, middle one, the area is much smaller than E. coli and Salmonella, okay? Because E. coli and Salmonella is gram-negative. The cell size is normally a little bit bigger. And Listeria and the Staphylococcus is mucosa. Cell is small. Another example, if you can see the maybe yeah, this one. The diameter, gram-positive Staphylococcus is mucosa, okay, round shape. And E. coli, the Salmonella is some rod shape. So this region, the size is like that. And also ratio, and the circle rod is most close to 1. This region, Staphylococcus, is much higher than the other 2 gram-negative bacteria. So it don't make sense. Once you got a feature, it's quite understandable. And also 3D scattering this intensity distribution, E. coli and Salmonella, the shape-wise very similar. So, but middle one, Listeria, especially Staphylococcus, really cosi, more round shape, to give us that kind of feature. Okay, so when you look at the spectra is still the most dominant, the most important feature in the Hypercube. So when you look at some, okay, let me speed up. When you look at 1D CNN, you just look at the spectra, and you can see the right side. This is actually, we just processed the data based on the SNEG profile. There are lots of difference. So this is based, actually using this kind of feature, we can just develop the model. And this is actually the result, classification result from FusionNet. If you use individual deep learning, the accuracy is quite a little bit lower than combined FusionNet. There's actual strengths, we just combine the 3 different deep learning model put together as a FusionNet, the accuracy almost 100%. However, when you look at a little bit detail in internal data, there is still the variability. This is actually collected 3 years, 2020, 21, 22. Even we got some good separate classification, different species, but some variability and when we just collect the data. So this is the most challenge. We have to develop a more robust model. So we just try to actually apply the different methodology, like a different algorithm based on the batch effect correction. So this is actually before the correction. You can see the second column and the first column. There are lots of variability, even though I think the same bacteria, okay? So we just applied, in that case, for example, when you just train the data 2021, the accuracy, classification accuracy very high 2021 because we trained the data, okay, that same year data. However, if we just apply the different year, 2020 or 2022, you see accuracy is drop at almost 61, very low. That means each year data has some kind of a bias. So bias correction is very important in this case. So we just apply the BC method called the batch mean centering or batch standardization algorithm. So you can see the second, the first, that actually adjusted all the variability together. So even though I think we just trying the 2021 and applied the 2020, the accuracy pretty high, very stable. So this is another things we have to consider. And when you collect a different batch, so we have to make sure the batch is biased or not. So that's a very important step in when you develop deep learning model as well. And finally, actually, we just collect all this information put together. This is actually the beta version of our commercial software. So we can just extract the single cell and then apply the deep learning model to classify our data. And also, this is a very good tool we can just separate, differentiate the live versus dead cell. None of technology can just differentiate the live or dead cell. Even PCR cannot do that. However, when you use the hyperspectral microscope data with the deep learning model, we can differentiate live and dead cell. Okay, this is a highlight. All right, in summary, we developed a deep learning model using the Hypercube, 3 different features quite well. Accuracy is very high, over 98%. Even we just corrected the batch effect and the biased data as well. Based on that, we continue work on that. Our ultimate goal to develop bacteria detection system without incubation. Okay, this is actually phenomenal. Usually, the data, the sample we collected here, we actually still use isolate. However, we just are developing the new method, collect a sample from matrix directly. How? We are working the microfluidics for bacterial sampling. So we just finished the simulation result, quite promising. So we fabricated the microfluidic device we are testing now. So once the microfluidics is completed, we can just collect some data, such as chicken coccus rinse directly, and they collect the bacteria, and you can take a look, collect the data from hyperspectral microscope, and the machine learning and the deep learning model applied it, we can classify or identify. Okay? I'm going to acknowledge my research group. Dr. Shin, Taesung Shin is developing program quite well. Nathan Bano, he's a technician, collect our sample. And I have 3 PhD students work with this research for their dissertation. Thank you for attention.